Thank you very much. So thanks a lot for the invitation. It's a pleasure to be in Vienna. I was supposed to come here in 2013 in September, and then my son was born late August. I was supposed to come here in 2016, and my daughter was born. So when I was invited here, I was slightly worried. And there is no third child, I'm happy to report. And well, here we are. So I will speak about the Counterspace. So I think that's pretty much on topic. Unfortunately, I don't know who chose the terminology Counterspace. If one of you knows, you can tell me. So Cantor came up with the Cantor set as a way to produce a set which was nowhere dense in the unit interval, but still of cardinality continuum. And this is very much not relevant to what we will be doing today. So Cantor set for me will be just the set of infinite sequences of zeros and ones. So there will be very little set theory in my talk. There will be a bit of descriptive set theory, and as you will see, a bit of failing at doing descriptive set theory. But so the main object is so-called minimal homeomorphisms. And this means that every orbit is dense. Equivalently, there is no non-trivial invariant closed set or no non-trivial invariant open set. Once you see the definition in this way, you notice that whenever you have a homeomorphism acting, say, on the Cantor space, there will always be minimal components, just because you take a minimal closed set, which is invariant. And sometimes these minimal components will be finite, and I will probably always forget to exclude finite sets from what I will say, but I'm not talking about actions of Z on finite sets, which are interesting, but maybe not very topological. Okay, so an example, well, you take the shift map, which takes some x and shifts the value by, say, +1 or -1. It doesn't really matter. The group is abelian. So this is a homeomorphism. It's not very minimal, right?
You are taking 2 to the z.
Oh yeah, 2 to the z. Thank you. Yeah, otherwise omega is not a group. That's a fair point. Indeed, in 2 to the z, so I'm shifting infinite sequences of zeros and one indexed by a group, because then I have a nice shift action. Thank you, Matteo. So this is not very minimal, right? There are fixed points, for instance, constant sequence of ones. And if you take an infinite minimal component, which exists, this is called minimal subshift. So there are plenty of those. They are interesting objects. They are very classical object of study in group theory. Of course, you may want to, to study subshifts, you may want to replace Z by any other countable groups and look at minimal subshifts for more complicated objects. Today I will stick with Z, because even with Z I don't know how to do everything I want to. So I had promised myself to go over the board slowly, because I'm very scared of erasing it. So let me use the bottom of the board. Oh, that's fine. So what do I want to say? A tuplet flow. So a tuplet sequence first. So it just means that, and I will not write, it has to be non-periodic, right? Again, everything will be non-periodic, infinite, and everything. So for any integer, there exists a period, such that for all k, so pi03 definition apparently, such that, actually G delta, such that for all k, x of n plus kp is equal to x of n. It's again in 2 to the z. Yeah, omega is equal to z today, I'm sorry. I don't know why. Okay, so what does this mean? It just means that if once you have a value, x of n, there will be a period depending on n such that this value is repeating periodically. Equivalently, any finite subword will occur periodically. And I will ask and not mention that there is no single p that works for everyone, that my work is not actually a periodic, my word is not actually a periodic word. So how do you build such objects? Well, you start with z, which I hear is infinite actually in both directions. And then you fill some values. Let's say 1 out of 2, I put zeros. And then I still have some space left. Let's say here I will put a 1. Here I'm still keeping some space because otherwise my sequence will be periodic, and so on and so forth. Right? So on even integers I put zeros. Then with period 4 I put a 1 here. Then with period 8 I can put something here. With period 16 I can put something further away. And that's how you build tuplet sequences in general. And as you can see, I can pretty much do it with, there is no reason why I played with powers of 2, it's just that it's simpler to explain. So these are common objects, and the reason why they are relevant here, an observation which I think is due to Williams, but it's, so this, I think, was introduced by analogy with tuplet matrices. I don't think tuplets did anything with these tuplet sequences, but I'm not sure. So the observation is that if X is tuplets and non-periodic, then the closure of its orbit under the shift, this is a minimal subshift. So these are examples of minimal subshifts. Okay, is that clear? So again, objects of study, not general minimal homeomorphisms, but actually minimal subshifts and even tuplets subshifts. So those that come up like this.
If you take a point in the closure but not in the set, and you take the object, you get out of this closure?
No, this is why it is. No, you stay in the closure, sure. Because just by continuity, if it's in the closure, the closure of the orbit will be closed, and so it has to be a closed subset of this bigger thing.
No, but if you take a point which is in the closure but out of the orbit.
Yeah, the closure will still be in there always. You will always have a smaller closure just by continuity. But what I'm saying is that the closure will be equal to the whole set. That's equivalently saying that it is minimal, is saying that whenever I take someone in this closure, the orbit closure remains the same for everyone. But not everyone is tuplets. Tuplets form a dense G delta subset. So not everyone is tuplets in there. That's okay. And what I would like to understand, thought I had understood and haven't quite understood yet, is the Borel complexity of orbit equivalence of these things. And I have to explain what orbit equivalence is. And first, I want to define the nice objects. Okay, now I will just preventively put these everywhere because it doesn't change everything. So the full group. So for those of you who've seen some ergodic theory talks, you might have met this in the ergodic setting. So the full group is the group of all, say G, all homeomorphisms, it matters, such that for all x, there exists some n which will depend on x, the G of x, let me call n of x. So what does this mean? It just means that G maps every phi orbit onto itself. It's a homeomorphism that maps every orbit onto itself. So there are those homeomorphisms that are automorphisms of the equivalence relation. You forget the dynamics, and you just want to respect the equivalence relation. Is the definition okay? So that's what the full group is. And even though I will not use it, there is an important object in geometric group theory, which is the topological full group. It's the group where you ask that this map takes only finitely many values, or equivalently that this map is continuous. Then these groups are nice examples of, they provided the first examples of what simple, finitely generated, amenable infinite groups by a famous result of Yushchenko and Mono. Here I'm not asking this map to be continuous. It will have some points of discontinuity. And just a remark that some of you heard me talk about a few years ago. This group is always, well, it's clearly coanalytic for all x, a nice condition, and it's not Borel. So there is some descriptive set theory here, and I don't know if it can be proved that it is pi11 complete. I mean, the proof gives pi11 non-Borel. It gives unbounded below omega 1, but presumably it's actually a theorem that this is pi11 complete, but I don't know that. Okay, and now I've been circling the board, dreading this moment, but well. Homeomorphism, the full group is not Borel. It's coanalytic and not Borel. In the measure theoretic setting.
So sorry, I don't understand anymore. Oh!
Oh, sorry, something I should have said. What does it mean that it is, what does it actually mean? It is a subset of the homeomorphism group of the Counterspace. I should have said a few words about this, thanks Ben. So, I should say what it means, what the topology even means, which gives time to the board to dry off. So that's, I will do this here. If you look at the homeomorphism group of the Counterspace, I said I would use Z. This is a Polish group, right? And what's the right way to think about the topology is that this is just, well, this is the same thing as automorphisms of the countable atomless Boolean algebra by Stone duality. This is the algebra of Klopen sets, right? And there is a unique Polish topology here, which is the one that comes from the convergence for the permutation group topology there. Meaning, two homeomorphisms are closed. If and only if they behave in the same way on a finite Klopen partition. And this is the unique Polish topology you can put on this group. Okay, so this is a Polish group, and now this full group sits inside. Oh, and here I have an omega. I have to chase every omega. You notice it doesn't matter. So this is a group which sits inside there, which has a definition which is pi11, just on the face of it, and it turns out not to be Borel. And this contrasts with what happens in measure theory, where full groups are always pi03 by a result of, what's his name? Wei? I'm not sure. A student of Alekos proved this in his PhD. And I didn't check the name, I'm not sure. Okay, so if you're bored during the talk, you can think of a way to prove that this is pi11 complete. Now, an important fact is that whenever you have any homeomorphism of a compact space, there will always be an invariant measure. So this is a classical fixed point theorem. If one wants to get fancy, one says that Z is amenable, or Z is abelian, and this works. So there is always an invariant measure. Invariant measures of minimal homeomorphisms are interesting objects. So do I want to give a definition? No? Okay. Let me first give a theorem due to Eli Glasner and Benji Weiss around 95. I failed here. So you take a minimal homeomorphism of 2 to the z, and then, let me introduce a notation. I will denote by k phi the set of Borel probability measures which are invariant. So this means that if I apply phi to a Klopen set, the measure doesn't change. Ah, thank you, Raphael. I saw your eyes. This will be a running joke. This was not intended. I'm sorry. So the measure is invariant. It means if I apply phi to a Klopen set, the measure doesn't change. And then if I apply phi to a Borel set, the measure doesn't change. But probability measures on 2 to the z, you should really think of them as finitely additive, as just being defined on Klopen sets, and then you extend them to Borel sets. You just think of them about what they do on Klopen sets. It's important here. And then we have one for any A, B Klopen, if any measure thinks that A is less than B, strictly less than B, then you can actually map A inside B. And here is when I point out that these things they are built out of gluing pieces of powers of phi together, right, informally. For any x, I use some power of phi. Okay, so then it's an easy exercise to see that elements of the full group must preserve every phi invariant measure.
Does the informing need to be strict?
It does need to be strict. If there is only one invariant measure, it doesn't need to be strict. And it's not so easy to come up with examples of minimal homeomorphisms with large sets of invariant measures. If you work on basic examples, you will get things that are uniquely ergodic. Right, this is the first example that come up. But as we will see, it could be that there are many, many invariant measures. Yes?
And I didn't miss what the star is for phi star mu.
So it means push forward. So phi star mu is the measure mu pushed forward by phi. The measure of a... Oh, okay, so if you don't know this, it's just, this is the measure nu, that nu of A is mu of phi minus 1 of A. Okay. You can always push forward a measure by a map.
So if the ultrafilters, if the measures are ultrafilters, then it's just the usual addition.
Yeah, this is sure, yeah. But these measures are not very much, they are nice Borel probability measures, right? They are very well behaved. No, they have to be regular enough. This is a compact set. This comes. Okay, this is where I show I'm not a set theorist. I come from functional analysis, but this is just inside of the dual of continuous function of 2 to the z. You look at the unit ball and you look at positive things that take the constant function 1 to 1. That's.
Yeah, I was thinking because if the group is discrete, then you get ultrafilters there.
But still, something I should say is that there are probably interesting questions when you replace 2 to the z by beta z. And you look at actions of z on beta z, and then you try to work out this type of problems inside there. And I have no idea what happens. I can preemptively answer all of your questions. If it's not trivial, I don't know what happens. But it's an interesting non-metrizable dynamical system. Obviously, z acting on beta z, and then what happens to invariant measures, what properties do you get, I don't know. I have never thought about it. But it actually makes sense to look at actions of countable discrete groups on their Stone-Church compactification. And I don't know the topic well.
If you just add the quality, how high complexity do you have to get before you get the injection in the analogous version of the full group?
So you would say that again?
So there will be a Borel. So if you just have the weaker thing where mu of A is less than or equal to
okay.
there will be a Borel one. Will there be like a delta 0 2?
I have no idea. I never wondered about it. I don't know. But you do need to do... wait. Will there even be a Borel one?
Yeah, the Borel one.
Yeah, there will be a Borel one, but the problem is that, of course, the image here will not be Kloppen. That's the problem. The G will be Borel, and so the image here will be a Borel subset of B, and not a Kloppen subset. So that's the problem, yeah, sure. So here, again, it's important that you work in the topological settings and with Kloppen sets, and it does change the flavor, because, say, this condition, assume that there is just one invariant measure. Just one, I'm just speaking about one nice non-atomic measure. Then if a set has measure, say, 1/2, just because the measure is non-atomic, it will contain Borel set with any measure strictly below 0, between 0 and 1/2, right? Whereas a Kloppen set with measure 1/2, even for an invariant measure of a minimal homeomorphism, typically think of a Bernoulli shift for the 1/2 measure. The Borel set has measure 1/2, and it contains, the Kloppen set has measure 1/2, and it contains no Kloppen subset of measure, say, 1/3. So this non-atomicity condition, it behaves, speaking about Kloppen set always imposes strong restrictions on the measure. So I don't know, I assume fairly low complexity, to be honest. Thinking of it, I think, I don't know. Okay, and the next thing is if you take for any AB Kloppen, the same assumption, but mu of A is equal to mu of B. So measures think that A of B are the same. Well, then this is the equivalent to, there exists someone in the full group that maps A onto B. Okay. So these are theorems of Glasner and Weiss. In this line, you can actually take the topological full group, for those who know what that is, and in this line, you cannot always take the topological full group. And this follows from that by an exhaustion argument, by some kind of back and forth argument. So the real theorem is here. Now a definition. I think the terminology comes from Heidi Dahl, who was a graduate student of Christian Skau. So it's from 2008. Dynamical simplex. If, well, there exists phi minimal such that K is equal to K phi, meaning there is some minimal homeomorphism which preserves exactly the elements of K. And the question at the time was, how do you characterize dynamical simplicity? Even if you take just one measure, it will not always be true, or it will typically not be true that there is a minimal homeomorphism that preserves it. So I will write a characterization once I finish destroying this board. So the first result about characterizing dynamical simplices is due to Akin, published in 2005, and it applies to singletons. So it says when given one, there exists a minimal homeomorphism preserving exactly that measure. It's an if and only if condition. Then there's a result of Dahl in her thesis that is slightly more general, but in particular gives you the result for finite dimensional simplices. So those with finitely many extreme points. And then the theorem I'm going to state, which was joint work with Thomas Ibarlucia, who at the time was in Lyon and is now in Paris 7. Gives you a characterization of this thing. So this was already a few years ago. So, and I forgot to say why I was particularly interested with these things in the context of orbit equivalence, but I will get back to it. So I'm not sure I will even have the time to say the word Fraïssé limit in this talk. That's a bit of a shame. So a set of probability measures is a dynamical simplex if and only if. Well, what are obvious necessary conditions? So if you look at the set of invariant measures for any phi, it's always closed. So the set of Borel probability measures is a compact set. So these have to form a compact subset. Similarly, a convex combination of invariant measures is invariant. So these conditions are true for any set of invariant measures for any group action. So far it's not about Z, it's not about anything. It's not even about minimality. I mean, this is just true for any set of invariant measures. Minimality is any element of K is non-atomic and with full support. So if you don't know what this word means, I'm doing very poorly on time, so I will not say anything. Essentially, these are mild non-triviality assumptions on the measures. It's not saying much, and it's still not about Z. This will be true for any set of invariant measures for any action of any countable groups, as long as the action is minimal. And the thing that is about Z, well, here you have a necessary condition, which is that for any A and B Kloppen, let's forget about the full group. I only have the measures. But the left-hand side of this implication says if for any mu in K, mu of A is strictly less than mu of B. And in the conclusion is that I can map A inside B by something that preserves all elements of K. So it means that there exists C. C is just this G of A. Kloppen, C is contained in B, and for any mu in K, mu of A is equal to mu of B, to mu of C. Thank you. I will hire you to always sit on my talks. It's perfect. Okay, so these conditions are all. So these two are obviously necessary. This one is necessary as soon as you know the Glasner-Weiss theorem. And it turns out that they are also sufficient. So this is the theorem with Thomas. And I should say the names that I should write the names. So again, Akin is the case where K is just one measure, a singleton. Then it's exactly this theorem. And Dahl is the case where you have a finite dimensional simplex. She has an additional mild technical assumption which turns out to be always satisfied. So this is this theorem in the case of finite dimensional simplices, and in some cases infinite dimensional, but with there is not clear whether then it became harder to show that it was always satisfied. Plus she adds the assumption that extreme points have to be mutually singular, which is also an obvious necessary condition if you know about the ergodic decomposition theorem, but it turns out not to play a part in the proof. Okay, and now we'll just say, because I spoke about Toeplitz shifts, so this is a new result. If in addition K is divisible, and we'll say what that is in a moment, then K is what I will just call a Toeplitz dynamical simplex. What does that mean? It just means that there is not only a minimal homeomorphism, but something which is conjugate to a Toeplitz subshift, which preserves K. Right? So if you want to know which sets of measures are preserved by a Toeplitz subshift, or something which is conjugate to a Toeplitz subshift, then you need an additional condition. I do not know an equivalent characterization there. This is an open question. But there is a sufficient condition, which is if K is divisible, then you can get a Toeplitz shift. Not just, here it says, if K satisfies this condition, then you can find a minimal homeomorphism preserving exactly K. If K satisfies an additional condition, then you can get a Toeplitz subshift preserving exactly K. And again, when I say a Toeplitz subshift, it's really something which is conjugate to a Toeplitz subshift. And what does divisible mean? It just means that for any A Kloppen and for any integer n, there exists B, which you may assume to be inside of A if you want or not. With this condition, it doesn't matter. Kloppen, such that the measure of B is equal to the measure of A divided by n. So you can divide for any mu. Sorry. So this means that you can divide all measures simultaneously by n. You can always divide them up to some epsilon by n. You can always find a b which has this measure, which is arbitrarily close to this measure. This is always true, but it's just not always true, even for one single measure, that you can find one that you can divide by 2. Okay, you can find, for a concrete example, k could be, I mean, you could have just one measure who takes value, on Klopen set, it takes values which are multiples of pi, say modulo 1. This can happen. And there you cannot divide by 2. I mean, you can almost divide by 2, but you cannot exactly divide by 2. It's just...
The Klopen B should be a subset of it?
Well, again, here it's as you want, because if you add this condition, B then has measures that are strictly less than A. But yeah, I mean, you should think of it as being a subset of A. I didn't write it because I'm lazy, but... I mean, it's... In presence of the other conditions, it doesn't change anything. And I've never used divisibility without these conditions, so... Okay, so now I can at least explain why I cared about these sets of invariant measures, away from the fact that, well, this is where I think I should put water on that, but I will not go there. I mean, that's just, I don't want to get overconfident. The board is still usable, so. So this is where I come to the most embarrassing time of this talk, which is that for those of you who were in the descriptive set theory meeting in Turin last year, I announced a result about the complexity in the sense of Borel reducibility theory of orbit equivalence of minimal homeomorphisms, which I will explain now. It turns out that this proof, which was written on pieces of paper, had a gap. I mean, okay, no, that's not right. It was false. It was just wrong. It was not a gap. So this just failed. And then I came up with what I think is a proof more recently over the spring, which means that there is an actual reduction. The problem is that at the moment I cannot encode it in a Borel way. So I will say a few words about it. I realized this week when writing down the final details that one of the operations needed the uniformization that I don't know if I can do in a Borel way. Okay, so I'm working back what was in my abstract. I'm not computing the Borel complexity of orbit equivalence of tuplet shifts. See, but I'm getting better. Last year I said I had and I hadn't. This year I say I haven't and I haven't. So, so now, what's the main object? I guess Fraïssé classes. So if you take two homeomorphisms, they are said to be orbit equivalent. Yeah, this time it can be omega. They are said to be orbit equivalent if, well, they have equivalent orbits, which means for any x and y, if x and y, I will just write a symbol for this and explain what it is. R phi means that there exists some n such that x is equal to phi n of y, or y is equal to phi n of x. So this is the equivalence relation associated to phi. And if you remember our definition of a full group, it really only depends on the orbit. So it's only something that depends on the equivalence relation. So that's what I'm looking at. So x is equivalent to y according to phi if and only if g of x is equivalent to y, to g of y, sorry, according to psi. Which just means up to applying up to conjugating, say, phi by a homeomorphism of my space, my two homeomorphisms have the same orbit. So orbit equivalent really means there are two conjugates which have exactly the same orbit. The dynamics may be completely different, but the orbits are the same. So you forget the dynamics, you remember the equivalence relation. So this is a very well studied notion in the measure theoretic world where there are nice results, and it turns out to be very different in topological dynamics. If you've seen talks in ergodic theory, all ergodic actions of Z are orbit equivalent. If they are measure preserving, they are all the same. Here it's very much not true.
Can you please write down RC?
So RC is just, so this means there exists n, y is equal to phi n of x. That's RC. So it's the equivalence relation associated to phi. So now a theorem of Giordano, Putnam, and Scar. The following are equivalent for phi psi minimal homeomorphism. One, phi is OE to psi, which is just phi is orbit equivalent to psi. So this is actually a way to not have to erase the board. I just write fewer and fewer words. I can condense the talk. So phi is orbit equivalent to psi, or there exists some G, say that these things are homeomorphisms again of 2 to the omega or Z, depending where we're at. Or there exists G, a homeomorphism of the ambient space, such that G pushes forward, as earlier, the set of, so remember this is the set of all phi invariant probability measures. So this pushes forward the set of G invariant probability measures onto the set of psi invariant probability measures. If you have an orbit equivalence between phi and psi, then either G or G minus 1, I'm not going to try to do this on the board, does that. Okay? So if you have an orbit equivalence, well, once you've conjugated and they have the same orbits, invariant measures really only depend on the orbit partition. So they also have the same invariant measures. That's all there is to it. So one implication is obvious, pretty much. The problem is that if you take two minimal homeomorphisms with the same invariant measures, they may very well have different orbits, right? It might even happen, for instance, that they have almost all the same orbit, except one orbit is split, of phi is split into two pieces for psi. This is a typical example. And there, if you want to prove that these things are orbit equivalent by a homeomorphism, so think about it, you have two equivalence relations, they are exactly the same, just an orbit of one has been split into two pieces, and every orbit is dense. Try to come up with a homeomorphism that mixes those things and maps one onto the other, it's very hard. And the proof is very much non-dynamical, it works using C-star algebras, and it uses dimension groups and the Efros-Randel-Mann-Chien theorem for those who've seen realization theorem for dimension groups. It uses a Toeplitz condition for dimension groups, which has nothing to do with Toeplitz sequences. But anyway, this is not an obvious theorem. And I forgot to say, I'm saying that the theorem is very hard and I don't give the names of those who proved it. That's just not nice. So it's a theorem of Giordano, Putnam, and Scar. I said that Glasner-Weiss was about 95, so I will say that this is about 94, because this is what motivated the paper of Glasner and Weiss. So this is the same time period, but just before. So applying Asger's comment, I will speak while I erase the board. The note here that on the bottom line, I get an action of the homeomorphism group of the Counterspace on the set of dynamical simplices. Being a dynamical simplex is a very nice Borel condition inside the set of compact, of closed subsets of probability measures. And here I have homeomorphism group of the Counterspace acting on this, right? Just taking one, shifting it. So here the equivalence relation that I see comes from an action of the homeomorphism group of the Counterspace. As I have said earlier, this is a subgroup of S infinity, and this action here is well behaved. So this means that this relation, in the sense of Borel reducibility, and given the time, I'm assuming that you all know what that is, this relation sits below the universal S infinity action. this reduces orbit equivalence to that relation, and conversely, in the paper with Thomas, taking a dynamical simplex here, we produce a minimal homeomorphism, which gives you the reduction the other way. So in terms of Borel reducibility, orbit equivalence of minimal homeomorphisms is the same as isomorphism of dynamical simplices. Okay? And these maps are, at least I will claim now that these maps are proved to be Borel. Proofs are typed down, and I looked at them and I believed in them. This is not the strongest endorsement, but okay. And now a question. I don't know who asked that question first. I learned of this question from Simon Thomas, so I will put his name here. Maybe someone else asked it before. What is the complexity in the sense of Borel reducibility of orbit equivalence? And I, of course, erase exactly the theorem that I had to use. So this is equivalence of minimal homeomorphisms, because then otherwise you can cheat and encode many things. Oh, and something that might worry you, which is the set of minimal homeomorphisms is G delta inside the set of homeomorphisms. So this is a nice Borel space, and I can speak about Borel complexity here. So here I have an equivalence relation on a G delta subset on a Polish space. And here I have an action of a subgroup of S infinity on a standard Borel space. They are Borel bireducible, and the question is what the complexity is. So now I will just, I guess, wave my hands about Fraïssé classes. So this is the beginning of my talk. Welcome. I'm very glad to be in Vienna. So I will just say, I guess, a few words. The thing is, this is, I think, the third time I'm giving a similar talk, and each time I'm surprised that I have only 5 minutes to begin the talk. The introduction takes me 45 minutes. I think I need to either learn or retire this talk. I will do the second, it's easier. So consider, so fix, now let me just fix a dynamical simplex. Okay, I will at least say where Fraïssé classes come up, and then wave my hands. Consider the structure in, definitely not a first order structure, but doesn't matter, which is, so on the counterspace X, 2 to the omega. So you consider the structure, which is the Kloppen algebra with the language of Boolean algebra, and all measures in K. So I had a function in my language for every measure in K. So this means for any A, I know how to compute mu of A for any mu in K. And what we have was that for any, so let me call this, I don't know, M, what we have was that for any AB, or any, oh, let me say this, any partial automorphism with finite domain, finite means a finite subalgebra here. So what's a partial automorphism with finite domain? It's just a map from a finite subalgebra to a finite subalgebra that respects all measures on this algebra, right? And this just means that I have, so let me do this with algebras with 2 elements. I have this, map here and map there. This has the same measure as here, this has the same measure as that. Okay, that's a partial automorphism. And what we said is, I can find an element, so this and that have the same measures, this and that have the same measures, meaning I can take an element of the full group, mapping this here, and an element of the full group, mapping this there. Gluing these two things together, I find an element of the full group that does that, but the full group is inside the automorphism group of that thing, because elements of the full group preserve all measures, not just the measures of this specific set. So any partial automorphism extends to a global automorphism of M. And this is what known in model theory as being an ultra-homogeneous structure. If you take a partial automorphism with finite domain, then it extends to a global automorphism. This is in an uncountable language, but the structure itself is still countable, right? The underlying set is countable. Now there is Fraïssé theory that says, and here I will not, I was really overly optimistic. So there is Fraïssé theory that tells you that if you have an ultra-homogeneous structure, you look at the class of its finite substructure. And conversely, if you take a class which satisfies this property, you can build an ultra-homogeneous structure out of this. So now what one can do, nice compact set, produce a certain Fraïssé class attached to it, and this is the topic of another talk. And from this produce the object that's known as the Fraïssé limit. What this will do is that using Fraïssé theory, you can start from a Choquet simplex, a nice compact convex set. You can apply Fraïssé theory to it, and then build as a limiting object a dynamical simplex inside of a Cantor set. And so I will just write, I guess, what one can do using this, because there is no way I can actually explain something in the mind. I do have only 2 minutes, right? Oh, and I had forgotten that this was filmed. This is very embarrassing. My life just took a turn for the worse. You know that sometimes my mom watches videos of me giving talks. I don't know how much English she understands, so hopefully she thinks I'm doing well. But, okay, let's see. If at Christmas dinner people are making fun of me about Borel reducibility, I will know where this came from. Okay, and so where we're at, and I guess, so this was supposed to be 20 minutes of my talk. So using Fraïssé theory, one can build a map that takes x from x closed inside 2 to the power omega, assigns to it a dynamical simplex kx, such that x is homeomorphic to x prime if and only if kx is isomorphic to kx prime, meaning there is a homeomorphism of the ambient Cantor space that pushes one to the other, which looks very much like a reduction of homeomorphism of closed subsets of the Cantor space to isomorphism of dynamical simplices. This relation here is S infinity universal by a theorem of Camerlo and Gao, I think published in 2000. So we are in good shape. This should be S infinity universal. The problem is that, as you can see, there is some work to be done into producing the reduction. What you're taking x, you produce a Fraïssé class that depends on x, then you have to take it to build its limit, and this has to be done in a Borel way, which I thought I had done, but at the moment, and this is my last talk, this map is only encoded in a sigma of sigma 1 measurable way, because at some point I need a uniformization and I don't know how to make it Borel. I think it can be done. I just realized very recently that there was a gap in this. So you can use Yankov von Neumann. You have a Borel set, you can uniformize it, and then that's it. The hope is that you can be more clever than I was and get a Borel uniformization or another coding. But still, there is an actual gap in a proof that I hope can be filled. So right now the theorem is there is a sigma of sigma 1 measurable reduction of the S infinity universal action. If you want, it doesn't cost anything to build a divisible dynamical simplex. And this, if you recall, which you probably don't, this is the same as orbit equivalence of Toeplitz subshifts. So here the hope is that this can be made Borel, and well, I have to get back to it. And thank you very much for your attention.